Hi, Elvis. Can I get a shout out if you can hear me?
Yes, I can hear you.
Okay, great. Thanks, Elvis.
Of course. I have a question, Professor.
Sure.
When's our first midterm?
Oh, good question. Let's see. I don't dread it as much as you guys do, but almost as much. Because I gotta prepare for it too. Let's see. It says, let's see, midterm.
It says week 6, but I don't know what week 6 is from here.
Good. Let me get back to you on that.
Okay, no problem.
Yeah. Is there a typical week that's like a typical, is there a typical midterm week? Like where all the midterms are at the same time?
I don't think so. All my midterms are scattered everywhere. Because
Okay,
there's like some classes are doing quizzes too, so
yeah. I did quizzes last semester and I don't know if I didn't convince myself it was any better than midterms. I don't know, we'll see. I think quizzes are nice because they don't let you fall too far off, you know, if you're lagging behind the class, but I don't know. Do you like quizzes better or midterms?
I would say quizzes. If I could replace quizzes for the midterms, I would like that.
Oh, yeah,
Because yeah, it's less knowledge you have to know.
that's
Like,
true.
yeah. And it keeps you up to date, I guess. Every material you need to know.
Yeah. Hmm. Yeah, I've done it both ways in this class. Hmm. Oops. Hmm.
Hello, Professor.
Yeah, hi, how's it going?
It's going good. How are you?
Good, thanks.
It's good to see you again.
Yeah, same here. Sorry for the long absence.
It's okay.
I won't tell you the reason for my absence on when was it? Last Tuesday, but on Thursday, because it's kind of comical. I for sure thought I was having a stroke. So
Oh, wow.
I ended up going to the doctor. This is what happens when you start getting old, man.
Oh,
You're going,
man.
hey, maybe I'm not gonna live forever. But it wasn't anything like that. But I was like, dude,
That's good.
this is the end. It's coming.
That's pretty scary, though.
Yeah. I think like once you start getting these thoughts in your head, like,
It just gets to you or something like that.
yeah, it's like
Oh,
you guys probably have the opposite feeling, which is you'll never be nothing's ever gonna happen to you guys, which is a good because you're young and
yeah, I guess.
makes us brave, I guess. But yeah, start getting old.
Yeah.
Go, whoa, every bad headache turns into a stroke. Okay, guys. So first, a couple of announcements. Let's see. So I think I had some previously recorded videos. They were on the canvas, but I hadn't checked the right boxes. So hopefully everything's there now that you guys can actually see from the previously recorded lectures. Usually I miss a few lectures here and there. I'm really sorry. They seem to be happening early and often this semester. So what I'm going to do is record lectures and start sort of record stuff for stuff that's coming, so you guys don't get completely scrunched for time. So I'm going to record after we get done with diode circuits. We're going to move to bipolar transistors. So I'm going to record a lecture on bipolar transistors, which we probably won't get done with diodes till hopefully early next week. So, and I'm put the bipolar transistor so you guys can, have some time to catch up at, at your own pace, relatively speaking, hopefully. So those two. And then we got to come up with a date for the first midterm. And so I'll come up with a date on Thursday and put an announcement for you guys. If, let me know. It's sort of pretty variable, whether it's, I think we have in the syllabus week 6. I don't particularly have a, particular date in mind at the moment, but if anybody who's got like a particular date that rather not do or rather do, let me know. I can't guarantee, there'll be people's, different people might have different needs, so I can't guarantee you'll get your wish, but at least I'll know if you have particular preferences. And then the last thing is I got an email about tutorials being available. I don't know if you guys are, tutoring being available, I guess is the right word. For the class, I'll also put that in the announcements in case you guys need it. So anyway, those are sort of the administrative stuff. Did you guys have any questions from an administrative standpoint? Anything? If not, let me give you guys a quick review of where we were. It's been like a week or so since we talked. So I think the important things I'd like to remind you guys of is we have this material that's the semiconductor material that we can create an excess of electrons and holes in this material. And so we can create this PN junction. Let me just try this. PN. How do I like to do this? NP. PN. I guess everybody calls it PN junction. So I'm going to make it PN junction. And so on the P side, we create an excess of holes, which, because we're not studying semiconductor physics specifically in this class, you guys can think of positive charges. Just think of it as positive charges. It's easier. And in the N-type material, we have an excess of electrons, which of course are negative charges. Okay, so that's the first device we can make with this. And this PN junction is also called a diode. That's the first type of circuit element we're studying in this class. That's a semiconductor. So the schematic drawing for this thing is this. Okay, so that's a diode, the same as, so this is the P side, this is the N side. Okay, and there are two conduction mechanisms in a semiconductor. There's one is so-called drift. That happens when electrons and holes, so this is holes are also, for some reason, have H plus as their symbol, electrons are E minus. This is like, you'll see this sort of going forward in your microelectronics and semiconductor classes. So electrons and holes move under influence of an electric field, of E field. So there's an electric field, and if you have a charged particle in an electric field, the electric field puts some force on the charge in the direction of the electric field, or in the reverse direction of the electric field, depending on whether it's a positive or a negative charge. Okay, so that's the first mechanism. It's electric field dependent, first conduction mechanism. The second conduction mechanism is called diffusion. And that happens wherever you have any particles that are free to move around. So those are electrons and holes move from high density areas to low density areas. Again, this has to do with like Brownian motion. There's no electric field in diffusion. There's no electric field. Just things, if you have an excess of electrons, they'll try to spread themselves out. That means going to places where there's fewer electrons. So they like to kind of evenly distribute themselves. And these two conduction mechanisms basically offset each other in a p-n junction. So right in here, because you have a nexus of electrons here, they'll try to go over here. And because you have a nexus of holes here, the holes try to go here. So you end up making this area, you're going to lose some of your negative mobile charges. So because you've lost some negative mobile charges, this area becomes positively charged. These are not mobile anymore, these charges. They're from the nucleus of these atoms that have lost their negative charges. So they're stationary charges. And this area, this area, P, becomes relatively negatively charged. And this is an actual physical area right around this so-called junction, which is where the P and the N meet. Okay. And so what happens is, as you get more and more positive charges going to the other side, this area grows, and so there's this area. And it turns out that whenever you have positive charges and negative charges, you're going to there's basically an electric field develops going from the positive charges to the negative charges. So just the fact that you have two stationary charges creates this electric field. And so this electric field is, so the diffusion current means electrons want to go from the N side to the P side, and the positive charges want to go from the P side to the N side. The electric field, it gets built, and it turns out it's working in the opposite direction to that. So it's trying to prevent that from happening, just because of the direction of the electric field that happens. It's the electric field pointed this way is going to try to push the electrons back to where they were coming from, and the holes back to where they're coming from. And at some point in equilibrium, what does equilibrium means? Means if you don't apply a voltage to this thing, you keep the temperature the same, you just let it sit there and wait long enough to see what happens. So in that point, these two things exactly cancel each other out. And so you don't get any current at this equilibrium point. Okay, so now but you have this built-in electric field. At that equilibrium point, there is an electric field, even though you don't apply any external voltage to this device, you still end up getting an electric field because the electric field is caused by these non-mobile charges, okay, that built up because things were moving in this direction and that direction. So that was the first thing that really confused me while I was taking this class. So you have this electric field, it just comes from these movement of electrons and holes originally, and you at this point are not applying an external voltage. Okay, just the thing is just sitting there, the diode is just sitting there. Okay, so now you can use this as a circuit element, this diode. Let's see what you can do with it. And try to go back to some of these facts. So this diode, if you put in, you can either, so in equilibrium, there's no current. Okay, if you apply no voltage to this thing, there's no current flow. So if I draw, let me draw a circuit here then with this diode. So I'm drawing, this is a voltage source. Let's call it VD. And put the diode here. Okay, and I'm going to call the current going through this as I sub D. So that's the current going from the voltage source to the diode and back. Okay, so then I'm going to draw a graph of what the current versus voltage looks like. So if we apply 0 voltage here, we're going to have 0 current, because at 0 voltage, there is basically, we're not applying anything externally. This electric field is keeping the currents from going back and forth. And so we get 0 current. Okay, as you apply, now you can go, you have one of two ways to go from there. Either you can basically make this a built-in electric field. This is called a built-in potential. This electric field this E field creates a so-called built-in potential. And so the voltage and electric field are related with E is equal to minus dV dx. Okay, so if you have this electric, so now you can either apply a voltage that increases that potential, makes it more difficult for these charges to go across, or you can make it more, reduce that built-in potential. Okay, so a positive voltage, if I apply, so since the electric field is pointing in this direction, the voltage is sort of like this, minus plus. So if I make this side more negative than this side, I'm increasing this electric field. Okay, so if I make this side more negative than that side, I'm increasing the electric field, means going in that direction. Okay, well, we already didn't have a current flowing. So what does that mean? So I guess we'll have even less current flowing, right? So what happens is you'll get a very tiny amount of current flowing here. That's I'm not going to get into the details of that, but it's a very, very small current. But it's essentially like you have no current flowing, but it's a very, very small current. And we call that I sub S, this very small current. And I sub S, and this is sort of flowing in a negative direction. This I sub S is something like, 1 times 10 to the minus 12 amp, 1 times 10 to the minus 15 amp, that kind of thing. These kind of ranges. So very, very, very small current. Okay, so that's one direction you can go to. The other direction you can go to is you can make this side put more like a positive voltage here on this side. So you can put a positive voltage here and negative voltage here. So you can try to reduce that electric field. And so now you're going in this direction. Now, as you reduce the electric field, you're going to allow this diffusion current to flow again. You're artificially allowing the diffusion, you're reducing this barrier, and you're letting electrons go across to this side and holes to this side. And this movement of these electrons and holes, it has a exponential characteristic to it, just the nature of diffusion current. So what happens is if you're going in this other direction, so if you're going beyond zero, you end up with this exponential characteristic, which looks like I sub s exponential of Vd over Vt minus 1. Okay, and in fact, sorry, this is just, let me just write the whole thing. So this whole thing ends up looking like, so for the whole thing, I is equal to I sub s exponential of Vd over Vt minus 1. I always draw this wrong, sorry. So actually I want to do this. The exponential is only for the Vd over Vt. And the parentheses is here. Okay, so Vt is just short for Kt over Q. K is something called the Boltzmann constant. It's a unit like a physics constant, universal constant. Q is the charge of an electron. I actually managed to remember that somehow, 1.6 times 10 to minus 19 Coulomb. And T is the temperature in kelvins. Not in Celsius. So Kelvin, so at room temperature, it'd be like roughly 300 degrees Celsius. Sorry, 300 degree Kelvin, I want to say. Okay, so Vt is at a particular temperature. You can think of Vt as a constant. And a good number to remember is at so-called room temperature, which is 300 degree Kelvin. Vt is around 25 millivolts. And our Vd is the voltage we're applying. Okay, so this is this equation that defines this curve. As you go in this direction, notice that Vd over Vt turns into, because the Vd is a negative voltage, this becomes an exponential of a negative value. So this quickly goes to 0, and this current becomes minus I sub s. So going over here, this current becomes minus I sub s. Going in this direction, because Vt is a small number, relatively speaking, is 25 millivolts, as your VD goes up, so let's say even if VD was, 200 millivolts or so, there's a factor of 10 difference between 200, let's say it was 250 millivolts, factor of 10 difference between 250 millivolts and 25 millivolts. So you get an exponential to the power of 10, which is like a huge number. It's a very big number. So this becomes much bigger than -1. And out here, you can just approximate this as being I sub s exponential of VD over VT. In other words, this -1 doesn't really matter out here very quickly. What else do I want to say about this? So, one of the things that, we look at, so this is sort of this equation that, you see a curve like this, it's drawn so that, I can explain that this is minus I sub s and this is exponential. But there's two things you got to remember here. One is that this minus I sub s, this I sub s is usually a very, very small number. So I don't know, it's like, I don't know if it's 10 to the minus 12, it's 10 to the minus 15, 10 to the minus 18 amps. These are all really, really small numbers. Okay, so if I was gonna look at this, I don't know if you guys have used oscilloscopes or whatever, but if you look at the oscilloscope and put a diode and put a voltage source across it and look at an oscilloscope, this guy's gonna, unless you really zoom in, really, really zoom in. A lot of times you can't even see this in normal scope. It just looks like it's zero. This is like really, really a small number. It's really, really a small number. So the only reason it's drawn like this is so we can talk about the fact that it's minus I sub s. Okay, and then the second thing is this guy, exponential. I would always look at these equations like exponential, etc., and it didn't have much meaning to me. But exponential, if you wanted to visualize it, it's a very, very steep takeoff. Very steep takeoff. So again, if you were going to look at this in an oscilloscope and a diode, what you'd see is something like, if you zoom in, you'd see that there is some kind of a sort of exponential curve here, but it'll look like just be like a straight line kind of thing is what it looks like. Although it's got an exponential function, but it kind of looks like this. This is again, sorry, VD and ID. So I wanted to point that out to you guys because it's, as you'll see, there's a approximation to this we can use to make our life easier sometimes when we're doing circuit design, and that's where this concept comes from, because this is really exaggerating. This drawing is really exaggerating how this is like zooming in way into this area to try to give us an idea about what happens. Okay, so that's a diode. So one of the things about junctions to remember, just as like a fact, let me actually just jump into this, sorry, first. So because of that, before I talk about areas, so because of that, this approximation, for ease of circuit design, we can actually do a very simple model of a diode, sometimes, again. And that's called a constant voltage diode model. This is called the exponential diode model. Which is, as far as we're concerned in the class, like this is the real thing. There's, in reality, it's a little bit more complicated. But as far as we're concerned, this is like physical reality. And then this becomes a simpler model, which is, again, comes from the fact that this is very close to zero, and this is like a very fast takeoff. So you can basically approximate it like that. And the way you look at it is, if VD is less than with this VD on, you basically assume the diode is an open circuit. So there's no current flowing. And if the VD is greater than VD on, so if you're here, you assume that the diode is a short circuit, but with a bias across it. And we'll see how, we'll do examples of this thing. But this is a approximation to this exponential model. Now, why do we need an approximation? So the reason is, as you guys will see, usually dealing with things like, when you're doing circuit analysis, you do a lot of build equations based on Kirchhoff's current laws, Kirchhoff's voltage laws, those kind of things. And so you're building these equations, you build up simultaneous equations, and you try to solve them like we had in the quiz. And what happens is, if you have to deal with things like exponential functions or things like that, it makes calculations very difficult very quickly. So this is like a painful thing to have to do. And the book, homework problems, etc., makes us do this a few times because you can't always use this approximation. But it basically saves you from having to deal with those exponential functions. Okay, so in your calculations. And it kind of turns you into, it's kind of a, how should I put it? It turns the calculations into a piecewise linear calculation. So instead of having one equation like this for your diode that describes both going in this direction and going in this, basically this equation describes a diode continuously, regardless of what V sub D I put in there. Here, it turns into a piecewise linear model, is that you have to decide, as the guy doing the calculation, if the voltage across the diode is less than this VD on, or if it's greater than VD on. So it's kind of that forces you into having to make that decision when you're doing the calculation. Again, we're going to get lots of examples of that. Sort of starting, let's see. Don't know what I want to say about this. Okay, so let me just say a couple more facts here. So there are times, again, so this constant voltage model is a simplification of the exponential model. And trust me, as you'll do the homeworks, etc., you'll see that it is a big simplification. But we need some techniques to help us analyze the circuits. But there are places and times where you cannot use this model. Okay. For example, this model does not have any indication of the area of the diode. So it turns out that if you increase the area of the diode, so assume that, for example, each one of these diodes has a current I sub S in reverse bias, or minus I sub S. If you have a diode, if they're connected in parallel, the total current is minus 2 I sub S. And in fact, if you have a diode that has twice the area, it also has a current of minus 2 times IS. But this model, this approximation model, there's no concept of like diode area or anything like that. It's just really, it's on or off. So if you have a circuit that's dependent on the ratio of sizes of diodes, and some circuits are like that, you won't be able to use this model. And so the other thing we'll learn is when can we use this model and when we can't use the model. All right, what else? Okay, so lastly, I think I want to talk about diode reverse breakdown. And we're not going to really use this in any of our circuits in this class, but when you take the lab, I think 2200 lab, or in the future in real world, you'll see this, is that typically this current is negative, this small minus I sub s here. So again, this is very small, very, very small. But at some point, I don't know if that's minus 10 volts, minus 20 volts. I don't know, it depends, each diode is different. The diode has this so-called breakdown. So you'll start conducting heavily because there is that basically, I won't tell you guys the mechanism, it's basically kind of like tunneling across this junction. But the upshot of it is you get this huge current flow. So you get this on, off, and then a huge current flow. So typically you do not, some circuits use this breakdown, some do, but usually you try to stay away from this place. Okay, so you have to kind of pay attention to that in the diode you use. So when you get it by a diode, you'll see things like the diode in the specification sheet. It'll tell you I sub s. It'll tell you the breakdown voltage, those kind of things. And again, typically, unless you're trying to use this break, and very few circuits do, try to stay away from that much reverse bias. Okay, and then there's different types of breakdowns. I'm not going to go into that. Just maybe for your own interest, you can look at different breakdowns, and there's Zener breakdown and avalanche breakdown, and they're used actually for, these are very special type of diodes that use these breakdown effects in some circuits, but that's getting kind of a little bit into the weeds for our purposes. Okay, so that's where we are with the basics of diodes. Any questions with that before we go to slide deck 3? Okay. Slide deck 3. So that was just the, sort of the basics of diode. Now we're going to start talking about actual diode circuits. What kind of circuits can we design from diodes? So that's what we're going to talk about. Let's see. I'm sure I got my notes here. So let's see. Let's move on to here. Okay, so this is an example of a diode application, which is something we're all familiar with, and it's a cell phone charger. So I don't know how familiar you guys are with this, but the power plug in your house or wherever we put in the power plugs actually has an alternating current, an AC voltage comes out of the power plug. What does the AC voltage means? You guys are probably familiar with some of this ideas, but basically, if you look at it with the oscilloscope or something like that, it looks like it's not like a constant voltage coming out of the power plug. It's a sine wave that's going up and down at 60 hertz. 60 hertz means that every 16 milliseconds, you go from peak to peak. Or every second, you get 60 of these peaks going through. So it's just constantly going up and down, up and down, up and down. So it's coming out of your wall. And the amplitude is pretty high. So we know like 110 volt plug is what you get in the US typically. In some parts of Europe or other parts of the world, it might be 220 volts. And so what that means is it's 110 volt RMS, root mean squared, which means the peak value is 1.4 or square root of 2 higher than that. So it might be 140 volts. roughly. So you get 140 volts, and 8 milliseconds later, you'll get minus 140 volts. I mean, it's a kind of a continuous signal, but it's this giant voltage coming out, relatively speaking, giant voltage coming out of your power plug just in your house, and it has peaks and valleys. Okay, so that's what's coming out of your wall. What your cell phone needs, though, your cell phone is an electronic chip, a lot of microelectronics. They can't deal with these alternating voltages. They want a nice constant voltage. So if this is looking at time, this giant swings of voltage coming from the power plug, and what your cell phone wants to see is something that's constant with time and a relatively low voltage. Okay, so this is what your when you get a little whatever I don't know what it's called, I guess a power brick, whatever it is that you plug into the wall and plug the other, plug in the other end of the USB to your cell phone. You want to somehow convert this guy to something that your cell phone likes. Okay, so the first thing you got to do is kind of drop this voltage down. You got to get this from, like, if you plug in 110 volts into your cell phone, it's going to blow up immediately. So the first thing you do is you put it through this thing called a transformer, which we're not going to really go to. You guys may have looked at it in previous circuits. It's basically two inductors that are magnetically coupled to each other, and that drops the voltage amplitude from, it can also step up the voltage amplitude, but the type of transformer that they built is going the other way. So it takes the 110 volt RMS signal and drops it down to 4 volt RMS signal. Okay, but you still have this 60 hertz oscillation, but now the amplitude is lower. So the amplitude, so something as simple as this passive circuit, I guess you want to talk about, the coil, inductors can drop the voltage down. But now you have the problem that you want to go from an AC signal to a DC signal. Okay. Now, the problem with an AC signal is it has no DC components. So a fully AC signal has no DC components. What does that mean? Well, if I take the average value of this signal, okay, so here's a sort of a drawing. If you take an average value of the signal, half the time it's on a positive, voltage. The other half it's on negative voltage. So if I take the average value here in one cycle, I'll get 0. There's no DC component to this signal. So the DC component of this guy is 0. Okay, so we have to somehow create a DC component out of something that has no DC components. And one way to do that is to eliminate one half of these cycles, okay, and just pass the positive cycles through. And if I just have positive cycles, and now I average, so one cycle, one would be this. So if I can somehow average this positive cycle, if I can keep the negative cycles from going through, I can actually get a DC component of just the positive cycles. Again, this is like one of the key applications of diodes is as a so-called rectifier. which does this function. I looked up where this word comes from, rectifier. It comes from rectification, which means like fixing. So it doesn't really say anything. You're just fixing, for some reason, this act of passing one polarity and not allowing the other polarity to go through is called rectification. So it's as if this is a rectifier. So what it's doing is just allowing one polarity of a voltage to pass and is blocking the other polarity. And imagine like trying to do this with a resistor or a capacitor or inductor. You just can't do it. You really need some kind of a transfer function. You need something that's like a switch, something that sort of allows it's on at some more than a certain voltage and off at less than certain voltage. So this is where you really need a non-linear circuit element. You can't get a resistor or a capacitor or something like that to do this, block one side off. Okay, so that's one of the primary applications of a diode. Now, any questions about that?
Oh, could you go back up for a second?
Sure, sorry, go back to
Okay.
this.
Yeah.
Okay.
All right. All right, I got it. Thank you.
Sure. Any other questions, guys? No? Okay. So let's think of it as like, as we said, when you have, where do they have it? Over here. So again, notice we said when in this constant voltage model, we said if the diode is from this point, we're going to pretend like it's a closed switch. And when it's less than this point, we pretend it's an open switch. We model, it's not we pretend it, we model it. In reality, there's a small amount of current flowing and it's an exponential profile. But basically in an ideal model, going below this, we assume it's an open switch, and going this way, we assume it's a closed switch. So going back to here, so if you have a diode somehow connected in the circuit in the appropriate way, when this thing is on a positive cycle, we can hook it up so that it looks like a closed switch, and when it's in a negative cycle, it can act as an open switch, and so on and so forth. So we only pass the positive voltage cycles to the output of the diode. So this is something, we have to hook it up correctly, but we can use a diode for this. Okay. So this is the input to the diode, and this is the output. Okay, and that's sort of your like different ways of looking at the diode. Again, as an ideal diode. The real diode is, there's like different degrees of abstraction. So we know a real model is a PN junction semiconductor. It has, this exponential characteristic and has this complex equation. But if we think of as an ideal model, we can just, this is, by the way, this is the schematic for a diode, whether it's ideal or not. But we can just say this is the P side, this is the N side. We can just model it at the simplest level as if you put more positive voltage here than here. You're operating out here somewhere, and it's like a closed switch. And if you put more positive voltage on this side than this side, it's working more over here where it's an open switch. Okay. And an interesting example is like, let's say if you were pretending like this diode is like a pipe, with a hinge in it or with a valve in it to conduct water. So if you have something like this, if the water current goes this way, it opens this valve and current flows. So that's would be analogy to applying voltage here. So it would be like having water or charges flow this way. Okay, but if you go the other way, if you try to force water in this way, the stopper sort of prevents the water, closes the valve and prevents water from flowing that way. So that's one way to look at it. So it's a pipe that allows water to only flow in one direction. So if it helps you guys to think of it like that, that's the important thing that a diode does. And an ideal diode, again, you're just pretending like this complex, relatively complex equation. It's not that complex, but it can get complicated if you have a bunch of diodes and stuff. It's just a simple function. Okay, so if you use that analogy, so now if you start playing with diodes, so hook them up in different ways. If you say, well, I have two diodes facing the same direction, this guy can conduct current this way, right? If you put A higher than C, you can get current conducting, and then that means that if A is higher than C, this turns into a short circuit. And if I make C higher than A, this turns into an open circuit, so it doesn't conduct. Okay, sounds good. If I hook up two diodes like this, so like face to face, I never get any conduction, because if I have this guy going high and this guy going low, if you look at what the voltages look like, this one of these guys is always basically open. So there's always an open circuit, and so both of these guys are always open circuits. Any questions so far, guys? No? Okay, so let's look at our ideal diode again. So first, there's three different models of diodes we'll talk about in this class. So we've got our diodes. There's three models. And the only difference between these three models is like they're trying to ease our calculation. So there's just simple, less simple, and much less simple. So the real model, is this exponential model. Model. Voltage versus current. Got this. I'm going to keep drawing this for you guys till you get sick of it. Exponential of VD over VT. I keep putting the parentheses in the wrong place. Yeah, that's the most complex model and the quote unquote real model. So one thing is right here, this guy needs, at zero, it's going to be exactly zero because of the equation there. Then the second one is the constant voltage model we already looked at. So simpler. It's called constant voltage. And that's pretending like this thing is just turns on at VD on. Past this point, it turns on. Before this point turns off. So this is VD, and this is I sub D. So this doesn't have an equation because it's a piecewise linear function. So basically you have to make a logical decision. So is VD less than VD on? Then if that's the case, then your diode looks like an open switch. Okay, and if VD is greater than VD on, the diode looks like a closed switch, but with a bias. Nope, I drew it wrong again. Sorry, guys. Actually, there's sort of a battery in series of VD on. The reason that battery is there is because when this guy's closed, you better have VD on across it, right? From a circuit standpoint, you have to be out here. Okay, so even a simpler model, so even simpler. So this is quote unquote constant voltage model. This is the ideal model. Which we just even get rid of this VD on and we just say if VD is bigger than 0, if VD is less than 0, then the diode is open. And if VD is greater than 0, then the diode is closed. It looks like it's closed switch. Okay, that's even a simpler model. And all it is you're just trying to make your calculations, your circuit analysis easier. And you got to decide, in this class, the problem, if you're taking a midterm, I'll tell you. If you're doing the homework, I'll tell you, or the homework problem will tell you which one of these models to use. But in the real world, you kind of, depending on the application, you decide which model to use. Okay. And you'd prefer to use this one if you can get away with it because it's such a simple model. But sometimes you basically have to revert to these things. So let's look at the ideal model, which basically looks like this. Okay, so we already did that. So if you're greater than, so VD is greater than 0, you get a closed switch. And if VD is less than 0, you get an open switch. Okay, so one thing is, why does this characteristic look like an open switch? And why does this characteristic look like a closed switch? Okay, let's pretend like we had a resistor. So in that case, if I draw VR, N is equal to IR, so I is equal to V over R, meaning that, let's say this, if this was the voltage current graph of a resistor, the slope would be 1 over R. Okay, so as my resistance goes down, as my resistance gets less and less, So I get closer and closer to a short circuit. Short circuit is zero resistance. So as my resistance goes down, this goes to, so R small, this goes to 1 over, say, 0, which I could say is like infinity. So the slope here gets sharper and sharper and sharper and sharper until it'll be, if I have 0 resistance, this slope becomes infinite. So it's a straight line. So meaning that this is implying this straight takeoff of current from voltage is saying that you have 0 resistance. You have a completely closed switch, a perfectly closed switch with 0 resistance. Okay, so here R is equal to 0. Okay, so that's what this sharp slope means here. Then on the other side is, as the resistance, if my resistance is going higher and higher, then this becomes more and more shallow, I guess is the way to look at it. Okay, until the point where as resistance becomes very large, you get to 1 over infinity, which goes to 0, which means that eventually, asymptotically speaking, at this very infinite resistance, we get a straight line. Okay, if my resistance, if this is like in case of a resistor, you get a straight line. So back here, you have a straight line when you have an open switch. An open switch is something with very high resistance, infinite resistance. Okay, so that's why you get this infinite resistance here and 0 resistance here. And that's the model. That's why it looks like that. Okay. Okay, so any questions about that? Okay, so now let's make things a little bit more complicated and interesting. So let's say we're going to use, circuit elements. They make things, they become really useful when you put a bunch of them together to do some special function you're looking at. And one of the most simple circuit elements that you're looking at is putting a diode in series with a resistor. So you're putting a voltage across a diode in series with a resistor. Okay, so if you were gonna use, let's see, what does this look like from a, let's say, KVL standpoint, okay? So from a Kirchhoff's voltage law standpoint, you have this voltage goes across this diode. So there's a, let's call this VD1. And then there's a voltage VR1. Okay, so VA has to equal to VD1. So if we take VA minus VD1 minus VR1 is going to equal to 0. So from KVL standpoint, VA minus VD1 minus VR1 is equal to 0, or VA is equal to VD1 plus VR1. Okay, now let's see VD1. What's VD1? Well, if you use the exponential model, remember that I is equal to I sub s exponential of VD over VT minus 1. Let's say I just approximate that I is equal to I sub s exponential VD over VT. So if I want to find VD1, I do let's see, what does that look like? That would look like V sub t, I'm just moving stuff around here, V sub t natural log of I sub a over I sub s. Remember, I sub s is a constant for a particular diode. So I'm assuming this constant current is I sub s, we'll just call I sub s for VD1. Okay, so I have this for VD1. It's equal to V sub a is equal to V sub t natural log of IA over IS plus the resistance, the voltage across the resistor is I sub a R sub 1. So if I try to figure this circuit out using an exponential model, I have to solve this equation. And because of this, now look at this, this is like the simplest circuit that, believe me, circuits get a lot more complicated. You rarely have something as simple as this. Right, so this is absolutely the simplest circuit we can come up with it. With a diode and another component, okay? Just a diode and a resistor. So just with that combination, you get an equation like this. And it turns out that because of this natural log and the way, you know, the circuit looks, you won't be able to solve this in a closed form. Okay, basically we're trying to get I sub a in terms of V sub a, etc. And you basically, as we'll see, you'll have to use like an iterative numerical method to get to a solution here. You just won't be able to get it in a closed form solution, okay, including the KCL value. So even solving something like this with the exponential model is pretty difficult. But now let's look at it if we just use the ideal model. So in the ideal model, we just set up ourselves with a piecewise linear analysis. We say, okay, if this voltage is negative, so VA is negative, my diode is in series with a resistor. If VA is negative, means this point is low compared to this point. So this point is low compared to this point. Then my diode is off. Okay, so I'm going to get a VA is negative. I'm going to get 0 current. Okay, and then you say, well, what happens if VA becomes positive? Well, if VA becomes positive, like this side goes higher than this side. And as soon as that happens, this guy turns into a short circuit. And all I see, so this guy becomes a short circuit, and all I see is the resistor. So I end up with a circuit like this. Okay, so I get, if VA is positive, I get the characteristics of the resistor, because that's all I'll see. The diode just turns into a short circuit, and all I see is the resistor. So I get this I is equal to VA over R characteristic. And as long as V is negative, I just see an open circuit. Okay, so basically you start looking at the circuit and saying, well, by analysis, I'm going to use, by inspection, I'm going to decide, like, basically this is an example of what you'll use all the time, is you'll see what happens, you start looking at what happens when VA becomes very negative or VA becomes very positive, and using this sort of piecewise linear approach. Any question about that, guys? No? Okay. So let's try this. want you guys work on this for a second. Now let's do the same thing. Oops. You guys try to take a crack at this. Trying to deal with this circuit. Vn is R1. I got a diode. Oops. Okay, so use ideal model. Ideal model. And come up with basically curve for VD over VD as a function of, sorry, ID as a function of VD. So why don't you guys take a crack at that for a second, and then we'll try to solve it together. It should take about 5 minutes to do that. Okay, guys. Anybody want to volunteer to help me solve this? I'll jump in at the same time. Okay, then I'll pick on Jihoon, who had a question. So hopefully this will help answer that question. Jihoon, can you help me solve this thing? Oh, you don't have a mic? Okay. So gonna throw somebody else under the bus, huh? Let's see, who else? Well, I'll ask Elizabeth. Elizabeth, can you help me out?
I'm not gonna lie, Professor. I'm still pretty confused.
Okay, no problem. Perfect.
Okay.
That's what we're here for. So to help you walk through this confusion. So let's first look at the ideal model. Okay, so remember the ideal model. If you have a diode, if this side is more positive than that side, it's a closed switch. And if this side is more negative than that side, it's an open switch. Are you okay with that? Just a real
Yeah.
simple, just take it on at face value. Okay, so the first thing we want to analyze here, or the first thing we try to do here is figure out, like, put ourselves in a clearly situation that looks like that or like that. So the first thing we do, this is like, we'll do this over, or you guys will do this over and over and over again. First, assume Vn is a very, very, very negative value. Just so there's no, if you assume it's like slightly negative, then there's some question of what's the resistance across here and so on. But if I assume Vn is like minus 1,000 volts or minus 10,000 volts or minus infinity or something, okay, which is an allowed value, I can just assume that, so there's no question of that this side, if Vn is very negative, so assume Vn goes to minus infinity, so very negative value. No matter what the resistance here is or anything like that, this side of the diode is going to be more negative than this side. There's just, if you're very, very negative, there's no question about it. This side is more negative than this side. So you're in a situation like this. Okay, this side of the diode is more negative than this side. And so the diode is like an open switch. And my suggestion is you guys do this every time. You look at that, just pretend like Vn is minus infinity. Okay, and then redraw the circuit. So if I redraw the circuit with a diode replaced with an open switch, I'll get that. You with me, Elizabeth?
Yep.
Okay, so if I was going to draw this functionality, what would it look like? So I want to do V in and V out. Right. So if I just had a resistor between V out and V in, what would this curve look like? What would I draw?
Would it be decreasing?
Well, so as this guy goes up,
Uh-huh.
right? There's no current flow across R1. So there's no voltage across R1. So as this guy goes up, this guy will just go up with it.
Mm-hmm.
Then there's no voltage drop across here. So it looks like I'll just go up. And if this guy goes down, it just goes down with it. And the slope here will just be 1. Because there's no voltage drop across this guy, it'll cross at 0. Okay, if V in is 0, V out will be 0. Okay, and because they're just following it, the slope will be 1.
Okay.
All right.
Mhm.
Okay, so that's a very negative Vn. Okay, so if I look at this guy here and draw it here, it'll look like this. Okay, so that's where this side will look like when Vn.
Why is there no voltage drop across R1? Because Vn is very negative, or
Well, why would there be a voltage drop?
well, since there's an open circuit, wouldn't the current just go straight to V out from Vn?
Yeah, but there won't be, like, if you had a resistor here, or something like that, you would get a current from here to here, right? You'd get a current going like this. But because there is no resistor here, it's just an open circuit here, you just won't get any current flow.
I see it. I get it. Okay,
Yeah.
cool.
Good question. So here at this asymptote, at the very negative value, you just get something with a slope of 1. Okay. So then we go the other way. We say, what happens if Vn goes to plus infinity? Again, you guys are going to do this over and over again in the homeworks and all that stuff. So in that case, if this guy, again, you're doing it because y minus infinity and y plus infinity is because this helps us without any controversy to figure out what the voltage is, whether it's more positive on this side, more negative on this guy, or more minus, more plus. There's no and, if, buts, and well, I had a resist, because other circuits, you'll have like resistors and different circuits here. So there'll be some question as where this crossover point will happen. But if you look at plus infinity and minus infinity, so for example, if this is plus infinity, then for sure this guy is going to be higher than this guy. Okay, the P side is going to be higher than the minus side. So it'll look like a closed switch. Okay, so it'll look like Elizabeth, are you following me?
Yeah.
Okay, so basically, again, so make the habit of, sorry guys, I'm running over, but let me just finish this. Take the habit of just redrawing the circuit too at Vn as plus infinity. Okay, so if I look at this, I have shorted V out. So no matter what V in does, right now, no matter what V in does, V out is just gonna equal to 0. So regardless of what Vn does, V out is just gonna be a straight line. So anything past this point, we're just gonna be a straight line. Okay. And the only way, so at the crossover point is when V out is equal to Vn. And the only place these two curves equal to each other is at 0. So you'll know that they'll be meeting at 0. So that's what this curve will look like. So it's got this function where at negative Vn, it's got a slope of 1, and at positive Vn, you've got a short coming out. That's kind of a procedure for analyzing these diode circuits. So I think in the next lecture, I'm just going to go over this over and over again with a bunch of different circuits and try to get your help till you guys are pretty comfortable dealing with it. June oh yeah, because June, you don't have a microphone. You're saying like ground? Yeah, it'll be like grounded basically. That's correct. Okay, any questions, guys?
So we're kind of solving it as like a piecewise function and then just putting together where VN is like very little and then where VN is very big,
Yeah, yep.
essentially.
And you're just, all you're trying to do is to stay away from doing this math. Or we'll end up doing this math for some functions, but as you'll see, it doesn't have a closed form solution. So it's an ugly process of guessing a voltage, guessing a current, guessing a voltage for VA, guessing a current for IA, and then sort of numerically solving it, which is pretty time consuming. So if you can at all get away with this, that's what you'd rather do. Okay, guys. So I will see you guys on Thursday.
Thank you, Professor.
Thanks.
Thank you.
Bye.
Appreciate it. Have a good one.
A good one.